Worked example 11, we are going to find the tangent to the curve where the gradient has a value of 8. So when we're finding tangents to the curve, in this worked example, we were using first principles. So let's go ahead and do that. So the first principle means f dash of x, we're going to use the formula, is equal to the limit as x approaches 0 of function of x plus height or some width value minus x itself over h. And so what we do here, it means it's the limit as h approaches 0, my bad. And what we're going to do is take the function, and the first part is x squared. So we're going to write x plus h all squared plus x plus h times 6 minus 8. So we've effectively done this part here, and we're going to subtract away f of x, so the function as it is, which raw function with just the x in it without the plus 8. So x squared plus 6x minus 8, and we're going to just clean that up now, and it's yet to be divided by h, so don't forget that bit. So the cleanup operation now is we're going to expand this bracket, the first bracket, so x plus h squared. I'm actually just going to write this all down to show you a better way of working, minus all of x squared with 6x with 8 over x. So I've just expanded that bracket, and now if I expand it right out to a polynomial, x squared plus 2xh plus h squared, and then we're going to expand out the second bracket, this one here, and that becomes 6x plus 6h minus the 8, and then we're going to minus away everything inside this bracket. So we're going to minus away the x squared component, we're going to minus away the plus 6, so it's going to become minus 6x, and we're going to minus the negative 8, which is the same as adding 8, effectively, all divided by h. Now from here on we have just a tidy operation. So let's find some nice highlighter and find some similar things to sort out. I can see that we have an x squared and a minus x squared, so they're going to cancel out. We have, where are we? X terms, we've got a minus 6 there and a plus 6 there, so they will cancel out. And I think that's possibly all we've got. We've got then following up, I'm just eyeballing it, xh and h squared. Oh, and the two numbers, we have a minus 8 and a plus 8, so they can cancel each other out. So in the second line, we're just going to write the bits out that weren't cancelled, top and bottom, 2xh plus h squared and plus 6h, and the 8's disappeared, h, and that is still the limit as h approaches 0. We can't just stick 0 for x in the bottom line because we can't divide by 0, but if we can factorize out the top line, so this differential, or f of x, I'm just going to write it better full working for you, f dash of x is the limit, is worked out by the limit as h approaches 0. So as we get rid of that little triangle to get it on the tangent, on the point of any point of this equation. And what I'm going to do is I can see in common there's an h in every term in the top line, so I can factorize that out. Let me just take it out and put the other factors in. So 2x plus h goes back in, plus 6 goes back in, all divided by h, and I can cancel, and that is equal to the limit, still as h approaches 0, of 2x plus h plus 6, and we're going to replace, is the word I'm looking for, h with 0. Therefore, that equals, so f of x, f dash of x is equal to 2x plus 6. Just take a pause for a moment there and remind ourselves that if we did this the shortcut method from the original function, which is this guy up here, by I, we would have had this a lot faster. So f of x, the original function, is x squared plus 6x take 8. And we've already done the drop each term at a time. So f dash of x is 2x to the power 1 plus 6, which is what we got here when we did it this ways. Next, we're going to look at what is the equation of the tangent where the gradient is 8. So the tangent line where the gradient is 8, I can tell you that an 8 gradient is a 1 along 8 up kind of a tangent, and it's whichever part on the curve has that particular steepness. Now, I don't know exactly where that is, but I know that the gradient itself equals 8. So what we can do with the derived function, that is the gradient function, we can set that to equal 8. So let's do that. So let's set f of x, f dash of x to equal 8. That means that this equation here, 2x plus 6, is equal to 8, which means that, so we're just doing the second part here, let's solve for x. So 2x is 8 minus 6, doing algebraic solving, it's 2, 2x is 2, therefore x is 2 over 2 is 1. So we have a point where x is 1 that makes that gradient true, and we're asked to find the tangent to the curve, the equation to the tangent of a curve. So this entire business here, the equation of the tangent to the curve, requires an equation to be set up. So what we know about this equation is that the point where x is 1 is where it goes through. It looks like it's on this line here. So if I hone in on here, that's my x is 1. At that point there, I'm actually going to get this slope here, this 8 up for 1 along slope. Visually, I did pretty good to kind of pop this little gradient in there, this little tangent. So I have that there, and it's going to hit in there, but we don't know its equation yet. So let's do the equation part to it. Equation formula. We discussed in classes y equals mx plus c is the general form of any straight line. And we know this is a straight line. It's a squared and a polynomial line for the curve itself. But any gradient function will be linear. It'll be changing as it goes around, which is why it's still a function. But it's a straight line, which is what this guy here is. And it's telling us that the function curve is 2x plus 6. But that is not the equation at the point of 8. So the equation of the point of 8, we're going to use the basis of this line here. And to find any line, we go general y minus a y point is equal to the gradient, which is m. And the x's, what we do for that part there is we have general x minus point x. So these x and y values, we have to substitute in a point for these ones here. So we know that x can be 1 from here. We don't know the point that corresponds to 1. So what we need to do is we need to substitute x back into the original equation. So we're going to write here, let's do this math method style. So we're going to write here the y coordinate where f dash of x is 8. Is such that x equals 1. Therefore, function of 1 going into, so we don't have a dash here, it's going into the original equation. I'm just going to write so a little bit more maths to explain it. The y coordinate where x equals 1 is we're going to sub it into f of x equaling our original equation, which is x squared plus 6x take 8. So we're going to put 1 in there, which is going to be 1 squared plus 6 times 1 minus 8. 1 minus plus 6 minus 8, negative 1. So the point for the tangent line runs through the point 1, negative 1. So that there can be our x1, y1 point, which we're going to substitute into the general equation for a straight line for our tangent. Yes, the question doesn't ask for the tangent line. It asks for the normal to the tangent line. But I'm just doing this just so you know and so that we can actually run this one through first. So the general equation is y minus y1 is gradient x general minus x point, y general. Now we're going to put this point in, -1, so it's minus -1, is the gradient, which at that point equals 8, x general minus x point of 1. Now if we rearrange this formula here, we'll get the equation of the tangent line itself. So we're going to use algebraic techniques to rearrange. So that's y plus 1. And I'm going to expand this bracket as 8x minus 8, which simply means that y is 8x take 8 take 1, which is 8x take 9. So that's the equation of our line at where the gradient is 8. I've entered this equation for the straight line into Desmos, and next to the original line I can see that this equation here certainly runs through the point 1, 1, and also it has 8 for the m in front of it, so that's its gradient. So a normal to the tangent is a 90-degree line. So a normal line is a line that runs 90 degrees to a specific line. So from our blue tangent line, it needs to go past the point where it kisses the tangent, which we decided was 1, -1. Let me find that. The scale's not great, but it is somewhere in there. So tangent normals have a pattern with the gradient of a line. If this is the gradient of my line here, then let's have a look at 1 along 8 up. The tangent to that line is going to be kind of like an inverse and negative. So it's going to be at 90 degrees, which we can use 1/8, the inverse, and it's minus. So the normal line has a negative tangent or opposite sign to where we are putting it normal through. So what we say is the gradient of the tangent is 1/m negative, and we know that m is 8 from this general equation, therefore it's equal to -1/8. And we also know the same point we can use, so that -1 point is the intersect of where the normal goes through. So that point we can use again, and all we're going to do is use this general equation, y minus y1 equals m, x minus x1. So for the normal line, normal's geometric term for a 90-degree bisector, so therefore y minus -1 is equal to -1/8 x minus the x point 1, and we're just going to algebraically rearrange this thing again. Minus 1/8 x plus, because we've got a minus there, 1/8, and we're going to bring the loose 1 onto this side as a -1 and tidy it up as best we can. So the first part of it, I'm just going to put -x/8. I think that's okay to make it just a wee bit tidier. And 1/8 minus 1, I'm just going to do some fraction arithmetic here. So 1/8 minus 1 is the same as 8/8, so that then we can calculate as a single fraction of -7/8, so it's -7/8. So I'm happy with that equation for the normal line to the tangent of the curve where the gradient is 8. Just an add-on, because it's a worked example, your textbook has this equation as x plus y8 plus 7 is 0. That's an acceptable form for a straight line. We just have everything on one side, the x term, the y term, and the constant term. I had y as the subject. If you choose to rearrange this, you'll get the same thing. So let's leave the y term on this side, and let's make the x term a minus x, and the 7, we're going to subtract it off both sides, so we get that. The y, we're going to divide onto the right hand side, the 8, so we get that, and we're best to split it up into parts. X over 8 minus 7 over 8 is a single y. So I can kind of see why the textbook leaves it in this form. It's a little more elegant. However, you can do a little more graphing and a little bit more with that one there. So either is fine, as long as it's the correct figures in there, which both are.